So having discussed failure assumptions of processes and channels, we now turn our attention to timing assumptions of processes and channels. Timing assumptions. So we are still in the specification of a service, and we are looking to the model. And now we will turn our attention to the timing assumptions, or the amount of synchrony in a distributed system. So when we talk about timing assumptions, we talk about timing assumptions of processes, of the network, and of the physical clocks that each process has. So what are the timing assumptions and processes? It is the bounds on time to make a computation step. And the timing assumption on a network or a communication channel is the bounds on time to transmit a message between a sender and a receiver. And when we talk about clocks, these are clocks local, physical clocks local to processes. We are talking about the lower and upper bounds on clock drift rate and clock skew with respect to real time. So let us look to the asynchronous distributed system model. And this unit will be about asynchrony and causality, as you will see why causality will be an important aspect here. So in an asynchronous system, there are no timing assumptions on processes and channel. We are not talking about, there is no bounds. So processing time can vary arbitrarily. This is because if you run a process in a server, the server could be overloaded, so we don't really know how long time it takes for that process to do some computations. And there are no bound on transmission time. And also, we assume that the clocks of different processes are not synchronized. So reasoning in this model is based on which event may cause other events. So causality is a very important tool when we are reasoning within the asynchronous system model. An interesting result that you will see is that the total order of events are not observable locally, which says basically the local processes do not have access to global clocks. So let us look to the notion of causal order. So what is a causal order? Sometimes it's called the happen before relation between events in a distributed system. So the relation, well, we'll call it happen before. We write it like this, and we index it by the execution. So this relation happened before on the events of an execution, or actually on a trace beta, which is also called the causal order, is defined as follows. So how it is defined. So if event A occurs before event B on the same process, then we say that A happens before B in that specific trace or execution. If event A is a sending of message M, so send M, and event B is a deliver of this message, so it's a delivery at some process, then we say that the sending happens before the delivery in that execution. We also say that A happens before B is a transitive relation, which would mean that if A happens before B and B happens before C, then also A happens before C. That's what we mean by transitivity. We say that two events, say A and B, are concurrent or potentially concurrent events if it is not the case that neither A happens before B nor B happens before A. And we write concurrent events this way. This is the way to write that A and B are concurrent. So let us look to this relation in a diagram. We have here what we call a time-space diagram. This is a way of visualizing an execution where we have a timeline for each process. So this is a timeline. And here's the first situation, which we say if event E1 is before event E2 on the same process, we say that E1 happens before E2, or E1 potentially caused E2. Here is the second situation when we have this diagram where event E1 is a send event by process P1, and event E2 is a delivery event to process P2. In this case, we say that E1 happens before E2. And here is a situation when you can see this transitive relation, where we have E1 is before, happens before E prime, E primes happens before E double prime, and E double prime happens before E2. Then we say that E1, of course, happens before E2. So this is really what we call causality of events. One event potentially cause another event, and this relation is transitive, as I just mentioned. So let us look at an example here, just to show what I just said. Here we have drawn a time-space diagram, and you can see here what we have. We have here an internal event for P1, and here another internal event for P2. These two events are concurrent in the sense that they are not causally related. If we look to this event, on the other hand, that I just mentioned here, so this event is after this event. And again, this is a send and this is a delivery. So you can see that this event, this one, and this one is of course causally related. Whereas, for example, this one and this one are concurrent. So some events are causally related and some are concurrent. Now we are going to talk about what we call similarity of executions. Whereas while the order of events in the different execution are different, but still each process in the system cannot distinguish the difference between these two executions. Okay, so let us define this properly. So first we define what is a view of a process. A view of a process Pi in an execution E. This will be denoted by this notation, E restricted to, by this bar, to Pi. So what is this? This is, you take an execution and then you take a subsequence of that execution E and you restrict it to events and actions and state of Pi. So whenever there is an event or an action or a state of another process, we remove it from the execution, but we keep the rest. We say that two executions E and F are similar with respect to process Pi if the view of Pi in E is exactly the same as the view of Pi in F. We also say that two executions E and F are similar if the execution E and F are similar with respect to every process. So saying it one more time, Pi sees the same state and the same order of events locally, which would mean Pi evolves in exactly the same way the two execution. And if that happens to all processes in the system, then we say that these two executions are similar. This leads us to what we mentioned here, what we call a computation theorem. So what is? It's talking about executions which are equivalent. And equivalent, it means that no individual process can observe locally the difference between the executions. Okay, so let us have a look here. So let E be an execution of this form. So this is the initial state. You do an event, you get to a new state. You do an event, you go to the next state. And V is the trace of that execution. So that's E1, E2, and so on. Now, let us take V, the trace, and change the order of events. So we say that P is a permutation of V, meaning that we have the same sequence of events, but we change the order of event. But P has a condition, which is it is preserving causal order. And what we mean by that. So if these are the events in P, so P preserves causal order of V when for each pair of events, so that event Fi happens before Fj, then in this execution of P, in fact, Pi always occurs before Pj in that sequence. So now what we have an execution E that results in a trace V, and we have a permutation of that trace that we call it P that preserves causal order. What we say then is that the execution E is similar to the execution starting at this initial state, but using the new trace instead. So what we are saying here is that in this new ordering of events, the processes do not observe a difference between that and the initial execution. These similar types of execution, we call them, they are equivalent executions. So what we are saying here is that if two executions, F and E, have the same collection of events and their causal order is preserved, then F and E are said to be similar execution. They are indistinguishable with respect to the view of each process. We can always change the order of executions as long as we preserve causality. So now, a set of executions that are similar, they form a group or a class, which is what we call an equivalence class, where every execution is similar to every other execution in the same class. The notion of an equivalent class is a mathematical notion, and it has the following properties. So the execution have the following properties in this class. They are reflexive. It means that each execution is equivalent or similar to itself. And the second thing, the property is symmetric, which says if execution A is similar to execution B, then also B is similar to A for any execution A and B. And it is transitive. If A is similar to B and B is similar to C, then it's the case that also A is similar to C. So equivalent classes is what we call computations. Okay. So let us see here a figure that illustrates similar or equivalent executions. So if you look to these three different executions, this is first execution, just drawn two-dimensionally with this time state diagram. You will and compare it with this one. So let's look first at the chain of causality here. You can see that these red events form a chain. The chain goes like this. This is a causality chain. If you look to the next execution, this one, you will see this causality chain is preserved here. Another chain we have is the chain of events on process P3. So this is another chain. So this is also preserved here. The same thing happens if we go and look to this third execution. So these three executions are different, but they are similar because events do not happen in the same order, but the causality chain is preserved. So all three executions are part of the same computation as causality is preserved. So let us now look to an important result in asynchronous distributed system. In fact, the computation theorem, which says that processes do not observe differences in different executions that are preserved causality, then can give us the following result. There is no algorithm in the asynchronous system model that can observe the order of the sequence of events. That is, can see this time-space diagram or the traces of all executions. So what we have said right now, the global order events cannot observed by any process in an asynchronous distributed system model, which also says that there are no such algorithms. You cannot write this algorithm to observe the global order of all events in an execution. So let us see how we can prove this. So now we are going to prove that this property, that there is no algorithm that can observe the global order of events. And we're going to do it by a contradiction proof. A contradiction proof goes like follows. You assume some property P, and you arrive to a contradiction, and then you can say, okay, P is false. So we assume that such an algorithm exists. We assume that process P knows the order of the execution in its final state. Configuration here means state. We take two distinct similar executions of the algorithm, preserving causality. Because they are preserving causality, then their final state at this arbitrary process P is the same. And that's what we say here, that the computation theorem says that the final repeated states are the same. Therefore, the algorithm cannot have observed the actual order of events as they differ. And that is what we want to prove. Computation theorem depended on the situation that processes can only communicate by message passing, and they can observe only the local state. So the computation theorem does not hold if the model is extended in such a way that each process can read a local hardware clock. And this is very easy to prove. So here we assume a distributed algorithm in which each process reads the local clock each time a local event happens. By a local event, it could be an input, output events, or an internal event. Then the final state of different causally preserving executions will be different because the clock values are different, which of course contradict the computation theorem.